Well, good morning then. We continue with what we were doing in the last class, namely we looked at the efficiency of C star due to distribution, then we calculated the time taken for a droplet to evaporate, we calculated the value of the evaporation constant lambda, and we said, well, C star due to evaporation also I can calculate, and we say that the total value of C star due to these two effects is equal to C star due to the distribution and multiplied by C star due to vaporization, and this is all about it. You get the efficiencies. I want to spend a couple of minutes on this vaporization. See, we told ourselves, well, lambda is a constant, it depends only on the properties of the fuel, and therefore lambda for a given, say, diesel is so much, like kerosene is around 0.2 millimeter square per second. If I have a hydrazine droplet in hot medium, it is something like almost 4 millimeter square per second. I can get the value of lambda. I can therefore say the time taken for a droplet in terms of d naught square divided by lambda. I know the time. That means d naught square, this has units of meter square by second, d naught square has units of meter square, therefore I get d naught square by lambda giving me the value of vaporization time, right. And the question of lambda, that is the evaporation rate constant, why do I call it as a constant? We find anyway dd square by dt, which is equal to lambda, which I call as evaporation rate constant, does not depend on any parameter, does not depend even on the diameter, it is just a function of the diffusion coefficient, density of the droplet and density of the medium, and therefore lambda tends to be a constant. Therefore, if you go to any lab which deals with combustion, they do experiments, they take a droplet, find out the time taken for vaporization, but then there is a complexity. This complexity comes whenever I have a droplet, it is in a medium, the droplet somewhat, when the medium is different, it tends to sort of absorb that particular gaseous medium on the surface, and therefore lambda is not really a constant at different pressures. At low pressures, well, it is a constant. At high pressures, I find that we did some experiments, in fact one of your seniors by name Balaji, he did some experiments, I would not say experiments, he did a series of computations on equilibrium at high pressures of liquid surfaces, calculated the value of lambda, and lambda at high pressure tends to decrease. In fact, his work was published in Physics of Fluids, and that is what we do research work on in combustion, evaporation rate, mixing and stuff like that. We found that lambda decreases at high pressures, but again it picks up at very high pressures, and we also find that at high pressures a droplet may become equal to a gas. That, in other words, if I were to plot something like a phase diagram, maybe I have a T and V diagram, I have the solid line, I have this line which is a liquid line, I have the vaporization line, this is my critical point. When I approach the critical point, and this critical point is not very high, for kerosene in oxygen it could be as low as 50 bar, but I operate my chamber pressure at very high pressures. At that time what happens is, maybe oxygen gets dissolved on the surfaces, the critical pressure increases in this binary medium, and still the droplet would still be in the subcritical case, and therefore this question of lambda is something which is important, in which lot of papers are written, and therefore I think you all should have a feel for it. I think this is all what I wanted to say. I will not go into these details in a regular class, but rather let us now come to the second point, namely what is it we have done so far. Let us take a quick summary. We started with tankages. We said liquid propellants are pushed into the chamber. I could have either a regulated gas pressure mode, I could have a pump fed mode, I could have something like a blow down mode and all that. Ultimately what is it I did was, I brought the fuel and oxidizer into the chamber, we looked at the efficiencies, we looked at the chamber, we have already looked at the nozzles, but what we have really not looked at is some of these pumps and turbines. In a gas generator cycle, we said I increase the pressure and then I pass it over here. Similarly over here what is it I do, I put a pump over here and then I pump the liquid over here, the second one, maybe this could be oxidizer liquid, this could be fuel liquid, this could be oxidizer pump, this could be fuel pump. And then what is it we did? We bled some amount of oxygen or oxidizer, some amount of fuel, burnt it in a gas generator, and then drove the two pumps. That means I put it into a turbine, I expanded the gases in the turbine, that means I reduced the pressure in the turbine, I generated power, I drove this over here, and when I took the exhaust gases and put it back into the chamber, I called it as stage combustion, and when I allowed the thing to go out through an auxiliary nozzle, I said it is a gas generator cycle. Therefore, maybe I should spend some little time on these pumps and turbines. Normally, the turbines what we use are of the impulse type. Impulse type means velocity. I just convert the enthalpy into high velocity gases, or rather I have something like enthalpy of the gases at the exit of the gas generator, that is at inlet to the turbine. I have at the outlet of the turbine the enthalpy, and this is converted into something like velocity. The velocity impinges on the blades, rotates the blades, and that is what drives the pumps. The pumps on the other hand, that means we say turbine is generally of impulse type. And how do we say this? We say, well, it goes as the resistance into something like a mass flow rate, R into m dot square is what gives me the particular power to run a particular turbine ring. This I just put as resistance. I will revisit this value a little later. Then I have the two pumps. Pumps, if they are small, if they are for a small engine, it could be a centrifugal one wherein I have small flow but I need high pressure. It could be a series of axial flow pumps, or it could be a combination of centrifugal and it could be a combination of radial and axial and all that. Therefore, several possibilities exist for a pump. And if you have to go into details of pumps and oxidizers, it becomes an exercise in turbo machines, and I will not go through it, but I also want to do some justice to pumps and turbines. Therefore, we find what is a pump required to do? A pump must generate some pressure, and what are the parameters which are there in a pump? Maybe the speed of the pump, so many n rpm, and generally pumps rotate at very high speeds of the order of 20,000 to 60,000. In fact, we have a new engine known as Vinci, which is almost like 1 lakh rpm is the speed. And why do we need high rpm? My dimensions must be small, therefore my speed must be large such that I am able to get a high pressure. Therefore, one of the factors is n rpm. The speed of the pump depends on the density, depends on something like a Q, that is the mass flow rate through the particular pump source, there is a factor. Maybe it also will depend, speed I said must depend on the dimensions, maybe a nominal dimension, like let us say diameter of the impeller or some mean diameter of the system. Therefore, we say that the head developed by a pump must be a function of a set of parameters. In other words, to be able to quantify the pressure rise in a pump, I need these parameters, and now I find that the number of parameters which affect the performance of pumps are delta P, the speed, the density, the flow rate, and this is quite representative. In other words, I am talking in terms of 5 parameters which are required to characterize a particular pump. And what are the 5 parameters I am talking of? I am talking of maybe delta P across the pump, maybe the density, maybe the flow rate, maybe the speed. Instead of writing in terms of n rpm, I rather put it in terms of radians per second omega, which is same as n, that means 2 pi n is equal to omega. And then the last parameter which I said is di. Now I want to find out the influence of all these things on delta P and vice versa. How do I do a complicated problem in engineering which involves a number of parameters? Dimensional, excellent. We have to do something like a non-dimensionalization or dimensional analysis. Therefore, let us do this. At least we say, yes, I have studied pumps through a dimensional analysis procedure. In other words, I am looking at the Buckingham pi theorem and telling myself I have 5 parameters for the problem. And Buckingham pi theorem tells me if I have a problem involving m parameters and having n primary dimensions to it, I can form m minus n non-dimensional groups. Right? This is Buckingham pi theorem. Therefore, what are the primary dimensions I am talking of? Well, when I look at this problem, delta p and rho, well, delta p and rho is a combination. Then I am looking at maybe q dot, maybe I am looking at omega, I am looking at di. Let us put the quantities here, delta p by rho, let us put the dimensions out, Newton per meter square into kilogram per meter cube, but Newton is equal to kilogram meter per second square. Therefore, this gives me unit as meter square over here, that means equal to meter square by second square here, and therefore the unit, let's put down the primary dimensions now. The primary dimensions for this problem are delta p by rho has unit of L squared by T square, length by time square. Q dot has dimensions of, yes, meter cube per second, that is equal to L cube by T, omega, exactly, yes, you are right, 1 by T, and we have di which is equal to L. See, I was very particular to do this dimensional analysis because in any subject we must know how it applies and we must be able to draw the conclusion, and here also we have a pump which involves some parameters. Therefore, how many fundamental dimensions do you have? L and T alone, that means 2 fundamental dimensions, and the number of parameters I have are 5. Therefore, I should be able to get 3 non-dimensional parameters. Therefore, I say for the case of pumps and turbines put together, or a or let us say a turbo pump, I want to develop pi 1, one non-dimensional, pi 2, pi 3. Then let's derive these pi 1, pi 2, pi 3, and then try to analyze, and let's see where how we can describe a turbo pump operation and how to go about making a turbo pump. Let's say we know the other things, why not we do this? Well, I go back and look at the problem. My 5 parameters are delta p, q dot, then I have omega and di. You know, even without doing a non-dimensional parameter, I can say delta p by, we also had rho here, delta p by rho. I know delta p by rho v square has units of pressure, and therefore I can write delta p by rho v square, or rather one non-dimensional parameter could readily be delta p by rho into omega square by di square. Just by observation. Why is that? I know rho v square has units of pressure, kilogram per meter square, then again meter square by second square, this gives me Newton per meter square. Therefore, by observation, let's do one by observation, let's do one by detailed analysis. Let's say, well, delta p by rho can be put in terms of a non-dimensional parameter, delta p by rho omega square di square, which is my first non-dimensional term. Let us do the second non-dimensionalization with for q dot. I have q dot 1, then I say, well, delta p by rho should also cause variation in q dot. Well, I have omega, I have to some extent already taken di in this, let me now put di as equal to 0. Let me not consider di, I put it as equal to 0, not being influenced, or rather I am looking for a non-dimensionalizing the value of mass flow rate in terms of, let us say, delta p by rho to the power a into omega to the power b, which I want to write as pi 2, because I am going to separately look at di a little later. If I were to look at this, what would I get? Should I really take this over here, or should I take something over here? Why should omega come over here? Let us keep this, or rather let me consider again, instead of putting q dot, if I am interested in, let us say, omega over here, and then omega I put in terms of, let us say, q dot to the power a, and let us put the other term delta p to the power rho to the power b, this could also be a non-dimensional parameter. In other words, I would like some non-dimensionalizing to be done for the speed of the system as a function of flow rate, and this, whether I can derive a non-dimensional term here, that means I consider pi 2 to be here rather than this value, and if I were to now erase it out and say my pi 2 is going to be here, what should be my value of a and b? How do I do this? I say omega has units of 1 over t, then q we just now told is units of L cube by t, meter cube per second to the power a, delta p by rho we had L squared by t square to the power b. This should give me a non-dimensional parameter, let us say pi 2 over here, it is non-dimensional. Now what should be my choice of a and b in this for it to be non-dimensional? Let us solve it. We find if I solve for L, I get minus 3a plus 2b is equal to 0, because I have to find out the value, because I want the net one to be non-dimensional, not depending on L and t. If I write the equation for t, I get minus 1, then plus a minus plus 2b, I bring t on top here, t to the power a and t to the power 2b, minus 1 is equal to 0. Therefore, what is it I get? I get 2b is equal to 3a. If 2b is equal to 3a, I get minus 1 plus 4a is equal to 0, or rather I get a is equal to 1 by 4. If a is equal to 1 by 4, the value of b should be equal to what? Yes? Now let's redo it, come on. L is equal to minus 3a plus 2b equal to 0. You have omega 1 over t, you have L q dot is equal to L cube by t to the power a q, you had L squared by t square to the power b, therefore I have 3a minus 3a, yeah, it is at the denominator, minus 3a minus 2b, yeah, you are right, minus 2b, because what I am trying to say is I swallowed a step. I have t to the power a into t to the power 2b divided by t into L3a L2b. Therefore, it is minus 3a minus 2b is equal to 0, and the next one is minus 1 plus a plus 2b is equal to 0, and therefore over here we should redo this. Let us do it. Therefore, I get 2b is equal to minus 3a, and therefore I get minus 1 plus a minus 3a is equal to 0, or rather a is equal to half. If a is equal to half, then the value of b is equal to 3 by 4 minus 3 by 4 minus and minus, that means I am getting, is it all right? Let us do minus 1 plus a, and 2b is equal to minus 3a, I have taken it on the other side minus 3a, therefore a is equal to minus 2a minus here I am getting minus 2a minus 1 is equal to 0, that means minus 1 minus 2a is equal to 0, or rather I get 2a is equal to minus 1, therefore a is equal to minus half. If a is equal to minus half, the value of b is equal to plus 3 by 4. Therefore, what will be my expression pi 2? Pi 2 is equal to, I get the value of omega on top, this was my q to the power a, which is minus half, and I have b is equal to delta p by rho to the power plus 3 by 4, or rather this tells me that the value is equal to omega root q dot, this should have been q dot here, divided by delta p by rho to the power 3 by 4, and this pi 2 is what we call as a non-dimensional speed or a specific speed. Therefore, I have got the second parameter. Therefore, let us put down the parameters together. The first parameter I said pi 1 is equal to delta p by rho omega square di square. The second parameter is says omega under root q divided by the value of delta p by rho to the power 3 by 4, which I now call as specific speed. I do the same analysis for finding out the non-dimensional di, and therefore I do this, and what is it I get? I will not do it in class, maybe you take it as a homework problem. Therefore, I take the value of pi 3, let us put it down here, this was pi 1, this was pi 2 which we call as specific speed, the value of pi 3 we will call as specific diameter, and that will come out to be equal to, I just write it out, the same thing we will follow and do it, otherwise it will eat into our class time. We call it as, we do the same exercise, all what I am saying is we will again write di pi 3 is equal to di divided by delta p to the by rho to the power a into q dot to the power b, evaluate a and b for I get a term like this, and the value what we will get is di into delta p by rho to the power 1 by 4 divided by under root q dot, flow rate. Well, these are the three non-dimensional parameter, we call it as ND or specific diameter. And the performance of the pump can be expressed as pi 1, which is this parameter, as a function of the specific speed and the specific diameter, and this is how we non-dimensionalize the parameter. But why did we non-dimensionalize it? Let us take one of the non-dimensional parameters and see what is the impact and why we are doing all this. When I say the specific speed ns is given by omega root q dot by delta p by rho to the power 3 by 4, and I call it as specific speed, and if I say specific speed of a turbo machine is something like let us say 0.6, what does it denote? Why is it so important? This non-dimensional parameter tells me for a given value of this diameter, if I were to scale up my diameter, I have to scale up the value of q, I scale up the value of the dimension, and all what I am saying is for a pump having the same value corresponding to the different sizes what I could have and different values of speed, the flow in the pump, the geometrical characteristics of the pump will be similar. In other words, for the same non-dimensional number, that is the same speed, if I say that non-dimensional speed is so much, then I can assume for different values of q, different values of diameter, for a given type, it could be axial, it could be handling a particular type of propellant, or it could be centrifugal, or it could be anything else, or a combination of some of the things. For a given axial flow machine handling a particular set of propellants, if I keep on varying the quantities and if I vary the size of it, if I get across a given number over here, the number is invariant, it shows that between the different types, that is one category of, let us say, an axial pump, if the size is varied, automatically q and d will get varied and speed will vary, q dot and d will get varied, and but if the speed, the specific speed is same, the flow characteristics and the geometrical similarity will be there, and therefore in all the pumps, all the systems what we use, for a given, let us say, a cryogenic pump, if it is axial flow, will have ns between a small range of variables. If I were to say the nd, that is the specific diameter, it will have a small range of variables. Therefore, if I have to scale up a cryogenic pump still using the axial pump, I will go ahead and design for this particular value of specific speed. Therefore, these non-dimensional parameters are powerful because they allow us to determine the range of operation of a particular system. Like what we said was, the speed of a pump may be 50,000 rpm, maybe therefore omega is equal to, let us say, 100,000 pi radians per minute, or to convert it by radians per second, I divide it by 60 and I get so much radians per second. And therefore, for this radians per second, if I were to get the equivalent value of ns, and how did I get the value of ns? I get omega, I get for that particular machine or particular pump, I find out the flow rate, I find out the pressure head developed by it, I get the value of ns. And now if I were to design another pump which has to cater for a much larger flow rate and a different size of it, if I get the same value of ns, well, the flow characteristics, that is the nature of flow in the system, that is the hydraulics in the pump, and also the geometrical characteristics will be similar, and therefore for a given type of pump, let us say axial pump, for a given type of propellant, the ns will fall in a very small number, maybe 0.6 to 0.7, and therefore these numbers are useful. And also the performance can be written in terms of ns, in terms of ndi, in terms of the delta p by rho omega square into di square, and this is why the non-dimensionalization is useful. But we always, whenever we plot the results of pumps and turbines, we always plot it as a function of specific speed. Anyway, dimension is one number in terms of delta p versus specific speed, and that is how the performance of pumps are measured. This brings us to the next part of our talk. We looked at the pumps and turbines from non-dimensionalizing point of view. The question is, what are the characteristics, what are the problems with pumps? See, we told ourselves, I take the propellant from a tank, I take it into a pump. Well, I cannot have high pressure in the pump, in the tank, maybe the pressure here is, let us say, 5 atmospheres, which is the upper limit. Now I feed the propellant into the pump over here and I take the outlet from here. This is inlet, this is outlet. There is a maximum pressure at which I can supply, because I have to carry a gas bottle here. If I have to increase my pressure, I have to increase the gas, which is not possible. Therefore, my pressure at the inlet cannot be high. Now if the pump is to rotate at very high speed, the velocity of the blades will be high. If the velocity of the blade is high, then the static pressure will be low. If the static pressure falls below the vapor pressure, bubbles of the vapor are formed, and bubbles of vapor formed will harm the blade. It will immediately go. We are rotating at high speed. These are things which go and hit the blade, and the blade gets damaged. Therefore, the pump is subject to cavitation, and in any pump it is necessary for us to reduce the cavitation. To eliminate the possibilities of cavitation, how do we eliminate it? My supply pressure or the stagnation pressure at supply, which I call as P naught, and this P naught, we are talking of a case when the maximum could be 5 atmosphere, minus the vapor pressure should be a large number, right? But this number depends on the speed of the pump. If omega is larger, well, my PV is same. What happens is the static pressure reduces to this value, and therefore my cavitation would start, and therefore this number becomes an extremely important number, and we say the net positive suction head, that is the net positive suction head, which is given by P naught by minus PV, must be a large number for any pump. Is it clear? Why we say I would like the net positive suction head, that is the P naught minus the vapor pressure, which we call as net positive suction head is P naught minus PV, or rather I can write this section net positive suction head as equal to, in terms of rho and g, as equal to P naught minus PV by rho g is the head, net positive suction head. And if I were to take this head, which I know for cavitation I need a reasonable number, and if I were to substitute in the value of the non-dimensional parameter pi 2, which we call as specific speed, and what was specific speed equal to? It was equal to omega root q dot divided by delta p by rho. I substitute delta p by rho, whatever I am getting at the pump inlet, as equal to something like omega into q dot divided by net positive suction head into the value of g to the power, this was here 3 by 4, I am sorry I gobbled it up. This value is what is referred to as NSS, that is, we say the specific suction speed for preventing cavitation, or we say this head must be this value must be a number must be such that cavitation does not occur, and we say this is equal to non-dimensional number with respect to cavitation. We call it, instead of writing it as NS, which was the specific speed, we say as suction NSS. Now, all what I am trying to say is cavitation is an important parameter. We would like the net positive suction head to be large, and therefore this NSS gives you an idea of what we need to do to make this a large number, or rather the specific speed must come down under the suction conditions. We tell ourselves, well, I would like the value of P naught minus the P vapor pressure to be a large number. How can you make this? Either the tank pressure must be increased, or else if I can subcool my liquid, if I cool my liquid, the vapor pressure comes down, I can still get a larger number. Or the third thing is, before the pump, that means I have a pump like this, I supply it. Before the pump I put another pump which I call as an inducer pump, such that when the main pump is rotating at very high speed, I get a higher value of P naught. That means I can improve the net positive suction head by the following three: either provide high pressure tankages which is not the correct solution, which is not possible. Second is lower the temperature of the propellants, in which case I reduce the value of PV, or I put something like an inducer ahead of the main pump. Therefore, people who work with liquid propellant rockets will talk of an inducer ahead of a pump, and this is the reason why it is done. I think this is all about turbines and pumps. We reduce the problem to one of non-dimensionalization. We talked in terms of a specific diameter, we talked in terms of a specific speed, and said there will be similarity when the non-dimensional parameters are the same, and we will be able to quantify the performance, and normally the performance is always expressed in terms of these non-dimensional parameters. I think with this background of turbines and pumps, let us come to the last topic, and I have been telling you earlier, whenever we have something like a rocket which is going up, and one of the functions of rockets is maybe you have the earth, the satellite must go around the earth in some orbit, and we said orbits are something like a freely falling bodies. We also told ourselves all freely falling bodies have a problem in that they are a case of in a state of weightlessness, right. Is it clear? We talked about it. Then now the question comes, I have a propellant tank, maybe a liquid fuel tank, an oxidizer fuel tank. Well, the liquid is at the bottom of the tank. I have a drain port through which I am drawing the liquid. If the rocket, as it is going with the satellite, or when the rocket is moving up, it is just coasting such that it is again in a state of weightlessness, it is not powered, then if the liquid is in a state of weightlessness, it is not going to be at the bottom here, it could be anywhere here, it could be distributed anywhere. And if it is going to be distributed anywhere, my act, even if I put a gas over here, I push the gas through a gas, I push the liquid, gas will come out through this rather than the liquid. Therefore, supply of a liquid under the conditions of, let us say, weightlessness is something to be taken care of. And how do I do it? I thought let us just take some pictures from the net. I downloaded some of them because it tends to be something which is important. You know, this shows one astronaut in one of the space shuttle services. You know, he is trying to eat something, but you know, the body, what he wants to eat is just freely floating. He cannot really, unless he releases his hand and comes back to it, it is not going to fall because it is in a state of weightlessness, right. You know, how do you drink water in space? This is again an astronaut, he is in the STS, the space shuttle system, wherein he has a water here and he wants to drink water. There is no way the water can come to him, he has to literally catch the water drop, bring it to his mouth and drink, otherwise he just cannot drink. And this is the problem we have of weightlessness. You know, I thought all of us being in combustion, this is how a candle flame looks like on ground, but if the same candle I light when it is in a state of 0 G, that is weightlessness, I get a beautiful picture like this. That means, you know, there is no buoyancy, because buoyancy depends on gravity. Since there is no buoyancy, the flame is beautifully a hemisphere over here. And this is the state, and therefore let us now come back to our problem of whether I can be, how do I supply propellants when I am in a state of weightlessness, and that is something which we have to do. This shows water droplets on some leaves in the International Space Station. These plants were grown there, and when you try to water them, you know, see water bubbles, this is the water drop on a leaf. This water drop does not have any mass here, I am sorry, does not have any weight. It has a certain mass, but weight is 0, Therefore, you see the leaf which is storing such a large quantity of water, because it is weightless, it just does not have a weight by which it can fall down, and therefore we come back to our problem. We have a gas bottle, we have the oxidizer fuel and the fuel over here, both are in the liquid state. When the flight is in a state of weightlessness, well, oxidizer could accommodate in any way and I will not be able to supply it, and therefore one of the measures which was done in the early part of the rocket technology was, I would have something like a diaphragm. What is a diaphragm? Let's sketch it out. You have something like a elastic material like the football bladder, something made of rubber, something like we have this harmonium in which we compress thing, that is a diaphragm, and this is something which gets squeezed. I put this in a tank, propellant tank over here, and enclose the propellant completely within. Now I pressurize it with a gas, and this fellow compresses the diaphragm, and the diaphragm as it compresses it keeps flowing. That means I contain the liquid positively, that means this is known as a positive expulsion system. That means I cannot leave the liquid free, I have the tankage, but within the tankage I must put a diaphragm, and in the diaphragm I stored fully the liquid, there is no gas at all, I make sure there is no vapor at all, and I positively push it through and the fuel gets expelled into either a pump or directly into the thrust chamber. That means both my tanks will consist of a diaphragm which is a positive expulsion system. Now diaphragm must be a very flexible material. One of the material used is EPDM rubber, is more or less universally used. What is this EPDM? It is a rubber type, it is known as ethylene, propylene, diene monomer. Why this rubber is chosen is, most of the upper stages, or let us say the rocket stages which are used in spacecraft, use the fuel hydrazine. Or MMH, and MMH is again monomethyl hydrazine, that is hydrazine based fuels, and this particular diaphragm material should not get dissolved in this particular case, because if it gets dissolved, even a trace quantities get into this, it may affect the performance later. We will study this maybe in the next class, wherein I will deal with monopropellant thrusters. A single propellant, can I use it for a rocket? What happens is, this will go and poison this, and this uses a catalyst, the catalyst will degrade, and therefore the general tendency is to use EPDM rubber for the positive expulsion system. But you see, the positive expulsion system has its own problems. You are having something like this rubber material, diaphragm material, and it occupies a volume, with the result the usable space is not fully used. That means the entire tank space is cannot be filled with the liquid, I am losing something. Therefore the current trend, and or what I must say is the more recent generation, by more recent I mean for the last 15 years or so, if not more, the thing is to use surface tension devices for feeding propellants, liquid propellants, for feeding, let us say, propellants at zero gravity conditions. All of us know what surface tension is. A surface, when wetted, things stick to it. Why does something have to stick to the surface? Well, you talk in terms of adhesion. I have a surface of a metal, I put a mercury drop, the mercury drop stays as a drop, it does not smear on the surface. If I put water on a surface, it smears. That means I say surface adhesion takes place. In this case, something like cohesion takes place. We do not want cohesion, but want the liquid to spread. It is not only the properties of the liquid, but the properties of the surface of the material are equally important. Like for instance, water spreads in a glass tumbler or in a vessel, in a glass vessel, but the same water does not spread on a lotus leaf. That means we are looking at surfaces, and how do I make use of surface tension to be able to overcome this problem? Well, I can think of the following. Let us do a small exercise. Supposing I make, let us say, a sieve, that means a series of things cross wire like this. Let us say I make spherical holes over here. I dip it in water. The thing is retained over here. How is it retained? Let us say I have maybe, now I sketch it, I have a series of holes here, and now I pour water, the water just sticks to the surface. Now I push air over here, maybe there is a value of pressure drop across this before which air cannot even enter it. That means I must overcome the surface tension pressure, and if I were to write, surface tension has units of Newton per meter, and what does it do? It wets the surface. I take an individual value, the diameter is d, the surface tension pressure is sigma, let us say Newton per meter into d is the value. Now I sort of push air into it, the force of pressure on this is equal to, let us say, the force of air which is being pushed in is equal to, let us say, P into pi by 4 d square. This is the perimeter, therefore this should have been sigma into pi d over here, and therefore this particular diameter can hold a pressure equal to something like, let us say, d and d gets cancelled, p comes on top over here, therefore something like sigma over p is equal to divided by 2 sigma by d, 2 sigma by r, because, or rather 4 sigma by d, or 4 sigma by d or 2 sigma by r, and therefore this is the pressure. Therefore if I can make some of these compartments here of a particular diameter, and then if I have a tank like this, and if I can contain in the tank a series of meshes here, and in these meshes liquid is always, whether it is gravity or not, surface tension does not depend on gravity, because it is just a pressure force at a excuse me, at a surface, and therefore what happens is, and I make sure that the gas pressure will not permeate through, I choose the diameter of these holes such that, then in that case this is always wet. Whenever I want to supply a propellant, the propellant is available. When I supply the propellant, immediately a thrust gets generated and the propellant which is there comes over here, and these are known as surface tension devices for supplying fuels at zero gravity. Let us take a look at some of them. See, this was what was done, but then I have a tank. I can also use these things for dynamic pumping. Let us say I have a tank like this. I put some devices like vanes which are on the surfaces. I enclose, I am able to contain this. I shape the vanes such that the pressure here is lower than the pressure here. In other words, the flow of propellant takes place, and I collect it in a surface tension device here, and I can supply it, and these are known as vanes. Let us take a look of them as has been used in some of the spacecrafts. Well, this is what I said. This is my area wherein I contain these screens or openings such that the fluid is retained there. These are the vanes through which maybe fluid comes over here. This is another view of it. maybe I have the vanes over here. This is the vane what I am talking of, this is the gap what I am talking of, this is where the sieve is there which collects the propellant and feeds it into the chamber. These devices have high values of expulsion efficiencies, that is most of the propellant can be expelled, unlike in the case of the positive expulsion system. This is all about surface tension devices. I think we have more or less covered the liquid propellant rockets, we considered the different elements, but just to get into one small part of it, let's what is it we said? We talked in terms of specific impulse, we talked in terms of mixture ratio, we talked in terms of different propellants. The propellants which we did not consider were maybe liquid propane, liquid methane and liquid ethane. When we compare the performance of liquid oxygen and kerosene, we find kerosene has lower performance than these cryogenic fuels, like liquid propane is normally a gas, liquid methane is a gas, and therefore people are trying to work on whether they should use some of these propellants in future missions, but it has still not become operational. And the last slide which I wanted to say was, when we consider a solid propellant, we added metal to solid propellant to improve the specific impulse. But if we try the same thing with liquids, what happens is the molecular weight of the products goes up, and putting metal in the propellant rather than improve the performance does not really give the advantage like you have solids. Therefore, metal in liquids does not seem to be a solution. The point one is higher molecular weight of the exhaust. Second is liquids required or metals require some more time to burn, and sometimes the metal comes into an oxide, but unless that oxide releases the heat, I do not get the energy, and that is where I gave you that assignment, wherein with dissociation let us calculate the products of combustion. It will illustrate the different type of problems we have. I think this is all about liquid propellants, and I think we have covered more or less of it. In the next class, what I do is I will talk in terms of monopropellant rockets and hybrid rockets, and then get into the problem of combustion instability. Right? Well, thank you then. I think that is about it.